Alright, so let's try to look at this space-time diagram here. This is the answer to one of your homework problems for what it's worth, but so here what I have is the way the space-time diagram works is the tilted frame is the moving frame coordinates, whereas the the straight ones are just the so this is the S frame, like the CT and X with S, and then the CT prime and X prime would be the S prime in the language of my lecture. And so here the idea is to look at two clocks that are originally in sync at the origin and let them they just stay put at the respective origins of their coordinate systems, which means that, well, it means for the moving clock it moves with the origin of the X prime, the S prime system. And then at time, a little bit time later, in the stationary frame of reference, we can compare the time that's elapsed in the stationary clock with the time that's elapsed in the moving clock, right, by looking at event A versus event B. And if you count in this diagram, you can count the number of straight lines that it's gone up. That's the number of CT units. So if you count, it's 1, 2, 3, 4, 5 up. But in contrast, if we count the number of slanted lines that it's gone up over here to B, I get lost if I'm not really careful. 1, 2, 3, 4, 4.3. So you see the time that the you could say the lab frame measures is longer than the time that the moving clock ticks. So the moving clock ticked yeah, the moving clock ticked 4.3 seconds. Sorry, I've got some stupid mental block about this. Every time I try to explain it, I get confused. But anyway, so here's the math of it. Event A in the, event A in the answer for the space-time diagram is literally just this picture I showed you. Excuse me. And so if you use I gave you guys a link. If you go to the link in the announcement, you can actually get this with these lines being blue and these ones being black, or vice versa. So if you have a color printer and you feel like it, you can do that. But anyway, so for event A, we'd have time CT. All right. So this has time. I'm saying that is time CT, and of course we're at x equal to 0. And event B, we're still at the same time. We're at time CT, but it's the origin, right? So how far has the origin gone in the S frame? Well, it's gone v times t, right? Because the moving frame is moving with velocity v by construction. So the coordinates for event B in the S frame are ct vt, and then I can calculate that same event in the primed system, right, using these the change of coordinate, the Lorentz transformations, right? And so if I put in t equals to big T and x equals to vt, then that gives me this. And then of course we should expect that x prime is equal to 0, right? That's because that's where we're putting the moving clock, and indeed that works out to 0. But then if you look at ct prime, you can do the algebra here, and what that gives you is gamma times 1 minus v squared over c squared. And after you play with these things for a bit, you'll recognize the algebra here. That is 1 over gamma. Actually 1 over gamma squared, because gamma is 1 over the square root of v squared over c squared. And so this simplifies to 1 over gamma, which gives you t prime is t over gamma, or as often we like to write it, t is equal to gamma t prime. So the time elapsed in the lab frame is gamma times the time elapsed in the rest frame of the particle. Or you could also call it the co-moving frame if you like. So there's that. There's also length contraction. So here's a picture for length contraction, and so you can compare the length of a rod, which is measured in its rest frame, right? So if the rod is moving, we call the frame which moves with the rod the rest frame, or the co-moving frame. So in the co-moving frame, or the rest frame, the length is L prime. But if you measure the length of that same rod in the lab frame, right, in which the rod is moving, you measure a shorter distance, because when you measure the rod, you measure it at the same time. And as you can see, if you trace the world lines of the beginning and the ending of the rod, they'd go like this and like this. So when you measure the length of the rod at this time, for instance, you get a shorter length as compared to that. And when you work out the mathematics of that, which I haven't, you get that the proper length, the length in its rest frame divided by gamma, is equal to the length measured in the lab frame. So this is called length contraction. I do have some calculations down here. These calculations down here just give you perhaps some more insight as into where these diagrams come from. It's really straightforward. It just takes a while to kind of like sort through it all. Basically, the idea is to graph the coordinate lines of the moving frame on the same diagram as the coordinate lines on the fixed frame. And so to do that, you need to figure out like the equations of the axes, like the CT prime axis and the X prime axis. So I just done that much. For example, the X prime axis has equation T prime equal to 0. So you put T prime equal to 0 into these, you get this equation and that equation. Not really interested in X prime, so I solve for it to eliminate it. That gives me this equation, which then I can solve eventually for this down here, which is CT equals V over Cx. You might recognize that as CT equals to beta x. So what that means is that the slope of the x prime axis has slope beta. And through very similar algebra, you can show that the equation for the CT prime axis is 1 over beta x. Now, for this diagram I have pictured right here, I did it for the velocity of the moving frame being half the speed of light. So what that means then is that this has slope 1/2, and this guy actually has slope 2, because 1 over 1/2 is 2. So that's how that goes. And if you play around with the thing I linked for you guys in the overleaf, that template, you can adjust this picture, and you could look at the space-time diagram for like 1/3 of the speed of light, or whatever you want really. Just tinker with the code a bit. So that's that. Now, let's see here. So just to be more specific, you can use what I just showed you. I just want you to draw it again for yourself. That is the answer to problems 82 and 83. I'm just looking for basically something similar to what I just showed you, and you don't have the business I did at the end about deriving the equations. That's not part of the solution. The solution is just the picture I showed you. All right, and you don't have to even have the full picture if you just draw the part which was of interest, the part I did in color. That should suffice. You don't even have to print out those things if you don't want to. All right. So I hope that's clear. Now let me give you a summary. Let me give you a summary of everything. So here's a summary. So special relativity. What did we learn? Well, the one thing I'm missing on this summary is the Lorentz transformations, but I assume you got those from class, so let's not worry about that. Because you do need to use the Lorentz transformations to solve the homework problem. Let's see here. It's pretty obvious which ones I'm talking about, but just to be clear, problems 80 and 81, these you want to use the Lorentz transformations. You just plug in what you're given into the appropriate Lorentz transformations, and you can answer the questions, okay? So there's that. Now, here's a summary of special relativity as I've covered it, all right? Basically, the main player here is this gamma. And gamma is this interesting 1 over the square root of 1 minus v squared over c squared, which becomes 1 if v equals to 0, but otherwise, it's going to multiply things. So the formula for length contraction we learned is the rest length divided by gamma. The formula for time dilation is the rest time, or the proper time, multiplied by gamma. I also talked about relativistic momentum in class. Now, I don't think I gave you guys any problems about that. But I would think that in your modern physics class, you'd maybe do some problems on relativistic momentum, since it's interesting and it's kind of neat. Now, I gave you a little bit of an indication of where 4 momentum comes from. It's from the rest mass times the 4 velocity. And I mentioned that the 4 velocity has this formula C gamma v. Now, the thing I was a little bit loopy on in class was I think I wrote this down though, but I wasn't sure about it. But it's right. The 0th component in the 4 momentum is actually the relativistic energy divided by c. And then over here you've got the relativistic momentum. Now the relativistic energy is m gamma c squared. As I mentioned in class, that if you use the power series, the binomial series here actually, to expand, you can get these are the first 2 terms for small velocity. And of course the rest energy is rather famous. E equals mc squared. You know, everybody thinks about that when they think about Einstein. But really E equals m gamma c squared. Less people know about this, but now you know. And of course this is the classical kinetic energy formula. Now, one of your questions about relativistic kinetic energy, and this is the formula for relativistic kinetic energy, you notice that I didn't tell you the mass of a proton, but that's because you can look it up. I recommend Google. Actually, I don't recommend Google. What am I saying? You can find it DuckDuckGo or what's that other one? I forget, but it's also in your book. Like, if you bought the book, it's mass of protons is, goodness gracious, if you got this calculator, let's see here, right there, mass of the proton, it's right there, I could look it up. Number 1. Why, that's number 1 on my calculator? Really? That is the most important constant in this calculator? For real? That's wacky. Now if I could just remember how to get to the constants in my calculator, then we'd really have something, wouldn't we? All right, come on. You can do it. Number 1, comp, equation, table. Man, no, that's not it. How do you do the I used to know how to do this constant thing. Oh, I think it's this one, const. And 1. Come on. Give it to me. I said 1. Well, I guess I have to do 0, 1. 0, 1. There you go. Mass of the proton. Apparently it's 1.6726215 times 10 to the minus 27. I believe that's in kilograms. So let's see. If the mass of the electron is, let's try the mass of electron, see what that is. What's the mass of electron is number, well, let's check the mass of the, well, that's neutron. Mass of the electron 3. Yeah, that's right. 10 to the minus 31, 9.11 times 10 to the minus 31 kilograms. There you go, that's the mass of the electron. Lovely. Now sometimes you'll see these masses given in terms of, well, let's not get into that. There's no need to teach a course of chemistry here. So anyway, that's the mass you need for that problem, okay? And then the other thing, the last homework problem you had was, more or less, it's based on this identity. And I never quite worked out the algebra in class, but essentially if you put in the Lorentz transformations, you can show that this quantity is equal between different frames of reference. And that actually still is true for other vectors, other 4 vectors, like the 4 momentum. It turns out it gives you this, it gives you, in the same way that this is the 0 component times c squared. Oh man, I need a c squared there. So, my bad. So it's actually just, that actually just ends up being minus e squared. And so if I'm, well, goodness gracious, I hope I got that right. Oh. Oh, no, my bad. Scratch that. It was fine like it was. So this is an invariant of different frames of reference. So in particular, you can calculate this quantity in the rest frame. In the rest frame, the relativistic momentum 0, and so you just get minus m squared c squared as it happens. So now one of you were asking me, how does energy turn into mass? And well, I mean, that's a complicated question. All I can tell you is that it does, I mean, it changed the course of World War II, right? We took about 3 kilograms or so uranium and we turned it into energy, and people noticed. So changed the course of human history, I suppose. But yeah, I mean, it can happen. It's not easy to explain. I mean, the full answer of how it actually happens involves physics beyond relativity, right? So let's see here. Then finally, I just got 2 quick examples to work through for you guys. So suppose a particle lasts 30 seconds while it's moving very fast, but it usually lasts 2 seconds before radioactively decaying. How fast is it moving? All right, so what we got here is that you've got 30 is the time in the lab frame, and you've got, excuse me, you got my bad. You got, it should last 30 seconds. Oh, good grief. So this is time dilation, right? So we've got 30 is equal to gamma times 2. All right. So that's the time that it's supposed to last. This is the time we observed it to last. So in its rest frame, it's experiencing 2 seconds. But actually, for us, it was 30 seconds. That suggests a gamma factor of 15. And so how do you figure out the speed? Well, then you got to do some algebra, which I wanted to show you since I haven't showed you yet. I think you guys could figure this out, but let's do it. V squared over c squared. So the natural enemy of the square root is the square. So square both sides, you get 225, right? Make sure I'm within frame. 225 is equal to 1 over 1 minus, I'm going to call that a beta, just because I'm sick of writing that. Beta squared, which then gives me that 225 minus 225 beta squared is equal to 1, which gives me 224 is equal to 225 beta squared, which then gives me beta squared is 224 over 225. So therefore, beta, which is v over c, right, is equal to the square root of 224 over 225, which tells me that v, the speed with which the particle is moving, was about c times the square root of, 224 over 225, which of course we could simplify the denominator to 15, but this is physics, so we'd like a number. Let me find it for you. Square root 224 divided by 225. I get 0.99, that seems wrong, 78 C. Is that right? Goodness. It feels wrong to me. Let me just try it out real quick here. So 224 divided by 225, all right, so 1 minus 224 divided by 225 equals that. Square root of that answer, and then reciprocal of that, 15. All right, yeah, it worked. Cool. So if you you gotta be careful with these. If you just try to approximate things, it'll go bad for some of these. Now this one here, if you measure a bus to be 2 meters long, the bus has a 10 meters length in its rest frame. How fast? So this is a length contraction problem, right? So we've got 2 meters is equal to 10 meters divided by gamma. So apparently gamma is equal to 5. So 5 is equal to 1 over the square root of 1 minus beta squared. Square this thing, you get 25. 1 over 1 minus beta squared, which then gives me 25 minus 25 beta squared equals to 1, which gives me 24 is equal to 25 beta squared, which then gives me beta is equal to the square root of 24 over 25, which says my velocity is c times the square root of 24 over 25, which is, now here's a hint, if you get a velocity that's faster than the speed of light, you know you did something wrong. So there's a pro tip for you right there. So your square root of 24 divided by 25, which is, yowzers, 0. This bus is really moving. 9, I'll give you 4 digits, 9798 C. So there you go. I hope that helps you with your homework, which is, by the way, due Wednesday. So continue enjoying your break. Thanks, guys.